Hello! In this video, we are going to prove the following theorem. If f is Riemann integrable on a comma b, then f is bounded on a comma b. Now, before we get into proving this theorem, let's first remind ourselves of some things. Let's consider our closed interval a comma b. Well then, a partition of a comma b is a collection of non-overlapping closed intervals whose union is a comma b. For example, this collection of closed intervals would be a partition of a comma b, and we might label these intervals I1, I2, and so on, and we might label the endpoints of these intervals x0, x1, x2, and so on. So in general, a subinterval II would be labeled xi minus 1, comma xi. Now a tagged partition is when we select a point from each subinterval. And let's say that the points we select are these. The points that we select are what we call tags, and we might label the tags T1, T2, and so on. So this would be a tagged partition of a comma b. And the way we can symbolize a tagged partition is with a letter with a dot on top. And in the collection, it's a collection of ordered pairs. The first coordinate of an ordered pair is the subinterval. The second coordinate is the tag in that subinterval. So this would be the tagged partition that we have above. Now, the norm of a partition is the length of the longest subinterval of the partition. So the norm of this partition would be the length of the subinterval I2. So in other words, it would be equal to x2 minus x1. And the way we symbolize the norm of a partition is with double vertical bars. So now, let's talk about the definition of a Riemann sum. Given f is a function from a comma b to r, and p is a tagged partition of a comma b, we'll say that these are the subintervals and these are the tags. Well then, the Riemann sum of f corresponding to p is given by this formula. So really what's going on here is we're adding the areas of a bunch of rectangles, where the width of each rectangle is given by the length of each subinterval, and the height of each rectangle is given by the output value of the function f at each of the tags. Right, so that's really what's happening here visually. So now, let's talk about the definition of the Riemann integral. By definition, to say that f is Riemann integrable on a comma b means the following. It means there exists a real number L such that for every epsilon greater than 0, there exists a delta greater than 0 such that for all tagged partitions of a comma b whose norm is less than delta, we have that the absolute value of the Riemann sum minus L is less than epsilon. Now, we have proven that the real number L, which satisfies this statement, is unique. And we denote the unique real number L by the integral from a to b of f. So we're going to replace L with this notation. Now, to say f is bounded on a comma b means the following. It means there exists a positive real number m such that for all x in a comma b, the absolute value of f of x is less than or equal to m. Okay, so now let's get into proving this theorem. Now to start with the proof, let's suppose f is a Riemann integrable function on a comma b, and we'll assume for a contradiction that f is not bounded on a comma b. Now, since f is Riemann integrable on a comma b, this means that this statement is true. And this statement works for every positive real number. So in particular, it must work for the positive real number 1. So taking epsilon to be 1, well then, there exists a delta greater than 0, such that for all tagged partitions of a comma b whose norm is less than delta, we have that the absolute value of the Riemann sum minus the integral of f is less than 1. But actually, it's going to be nice if we change this up a little bit. We know from the reverse triangle inequality that the absolute value of this quantity is greater than or equal to the absolute value of the Riemann sum minus the absolute value of the integral. But every real number is less than or equal to its absolute value. So in particular, this real number must be less than or equal to its absolute value. So this shows that the absolute value of the Riemann sum minus the absolute value of the integral is less than 1. So adding the absolute value of the integral to the other side, we get absolute value of the Riemann sum is less than 1 plus the absolute value of the integral. So from this inequality follows. Now certainly, there exists a partition of a comma b whose norm is less than delta. And to see why, well, from the Archimedean property, there exists a positive integer n that is bigger than b minus a over delta. Right? Given any real number, we can always find a positive integer bigger than that real number. So then, dividing n to the other side and multiplying delta to the other side, we get b minus a over n is less than delta. Well then, the partition of a comma b with n equal subdivisions will have the length of every subinterval less than delta, and therefore the norm of that partition is less than delta. And so let's call that partition Q. Now notice, we have not given any tags to this partition, but now we're about to choose tags for this partition, which will lead us to a contradiction. And so to do that, the idea is, since f is not bounded on a comma b, well then there's no way that f could be bounded on every one of these subintervals. Because what happens if instead f is bounded on every single one of these subintervals? If f is bounded on all n subintervals, well then, since f is bounded on the first subinterval, this means that there exists a positive real number I'll call m1, such that the absolute value of f of x is less than or equal to m1 for all x in the first subinterval. And we would have the same thing happen in the second subinterval. Instead, I'll call that positive number m2. And so on, all the way up to the nth subinterval. But then, from this information, we could show that f is bounded on a comma b. Because, in that case, we'll take m to be the maximum of m1, m2, and so on and so forth up to mn. Well then, with this choice of m, we can show for all x in a comma b, we have that the absolute value of f of x is less than or equal to m. So to prove that, we would give ourselves an arbitrary x in a comma b. Well, since x is an element of a comma b, and q is a partition of a comma b, then x must belong to one of these subintervals. So let's say that x belongs to the ith subinterval. But remember, f is bounded on every single subinterval. So f is bounded on the ith subinterval. Because f is bounded on the ith subinterval, well, based on how we chose each of these positive numbers, it follows that the absolute value of f of x must be less than or equal to mi. And mi is less than or equal to the maximum of all of these, and that is our choice of m. So this shows, with this choice of m, then given any x in a comma b, we have that the absolute value of f of x is less than or equal to m, and so we've shown that this statement is true. So that shows f is bounded on a comma b. But that contradicts our assumption that f is not bounded on a comma b. So assuming that f is bounded on every single one of these subintervals leads us to a contradiction. So we must instead have f is not bounded on at least one of these subintervals. And we'll say that it's the jth subinterval. Now to choose tags for our partition Q. Turns out it's only going to matter the tag that we choose for the jth subinterval. And for all the other subintervals, it's not going to matter. So for all the other subintervals, we're just going to choose the tags to be the right endpoints of those subintervals. So then what should we choose the tag of the jth subinterval to be? Well, since f is not bounded on the jth subinterval, this means we could choose the jth tag in such a way that the distance from f of tj to the x-axis is arbitrarily large. And therefore, when we look at the Riemann sum, well then, that means the area of the jth rectangle can be made arbitrarily large. And so in that way, there's no way it's guaranteed that the Riemann sum is bounded by this value. And that is what's going to lead us to a contradiction. So, to see how we choose the jth tag, well, no matter how we choose the jth tag, the resultant Riemann sum is going to have to satisfy this inequality. So no matter what we choose the jth tag to be, this inequality will hold no matter what. But then, by definition of a Riemann sum, this Riemann sum would be equal to... But then, if we isolate the jth term of this sum, well then we would have this. But now, we see that this is in the form absolute value of a is less than c. But by properties of absolute values, this is equivalent to saying that a lies between negative c and positive c. So that means the quantity inside this absolute value lies between the negative of this quantity and the positive of this quantity. But now what we're going to do is we're going to solve for f of tj in this middle expression. So focusing on the left-hand inequality, we're going to subtract this sum to the other side and divide xj minus 1 to the other side. And we would get this. But then on the right-hand inequality, we're going to subtract this sum to the other side and divide xj minus 1 to the other side, and we would get this. But notice, this quantity on the right-hand side must be less than or equal to this. Notice, we've modified the middle term. I forgot absolute value bar. We've modified the middle term to this. And the property we're really using here is that for any real number a, the negative a is less than or equal to absolute value of a. So in that case, the negative of this sum must be less than or equal to positive absolute value of the sum. Well, from there, that implies that this entire thing must be less than or equal to this entire thing. And by similar observation, this quantity must be greater than or equal to this. And notice we replaced the third term with this. So the property we're using here is that negative a is greater than or equal to negative absolute value of a for any real number a. So in that case, the negative of this sum must be greater than or equal to the negative absolute value of the sum. And so because of that, that implies this entire thing must be greater than or equal to this entire thing. And if we pull out the negatives from the numerator and pull it to the outside of the fraction, well then we get this. So then this guy is less than f of tj, which is less than this guy. So this is of the form negative c is less than a is less than c. But remember, by properties of absolute values, that's the same thing as saying absolute value of a is less than c. So this means the absolute value of f of tj must be less than this guy. So no matter what we choose the tag of the jth subinterval to be, it'll always be the case that absolute value of f of tj is less than this quantity. But f is not bounded on the jth subinterval. And what does that mean? It means the negation for f to be bounded on the jth subinterval. But what is the negation of this statement? The negation is to say, for all positive real numbers m, there exists an x in xj minus 1 comma xj such that absolute value f of x is greater than m. So this statement works for every positive real number. So in particular, it must work for the positive real number that we have right here. So taking m to be this quantity, there must exist an element in the jth subinterval, which we are going to take to be the jth tag, such that absolute value of f of tj is greater than this guy. But doing the analysis we just did, we can also show that absolute value of f of tj is less than that quantity. So at this point, since we've chosen all of the tags for our partition Q, well now we have a tagged partition, Q, along with the tags that we've just chosen. And remember, the norm of Q is less than delta. So from way earlier on, when we introduced delta into the proof, well, since the norm of Q is less than delta, this implies that the absolute value of the Riemann sum must be less than 1 plus the absolute value of the integral of f. But then, by definition of a Riemann sum, we know that the Riemann sum of f is going to be equal to this. But then let's extract the jth term of this sum. So we have this, but then we basically are doing the work that we did earlier. this is in the form absolute value of A is less than C. And therefore, the quantity inside these absolute values must be between the negative of this value and the positive of this value. But then, as we did earlier, we took the middle expression and isolated f of tj. And to do that, for the left-hand inequality, we subtracted this sum to the other side and divided xj minus 1 to the other side. And we did the same thing for the right-hand inequality as well. But then, for earlier, we also saw that this quantity is less than or equal to this quantity, right? But then, from earlier, we saw that this quantity is greater than or equal to this quantity. And then, let's pull the negative sign to the outside of the fraction, which means we get this. But then, this is of the form negative c is less than a is less than c. And therefore, we must have absolute value of a is less than c. Or in other words, we have absolute value of f of tj is less than this quantity. But remember how tj was chosen. Tj was chosen so that absolute value of f of tj is greater than this quantity. So we have absolute value of f of tj is greater than this quantity. So this shows absolute value of f of tj is less than absolute value of f of tj, which is absurd. And so we have reached a contradiction. Our assumption that f is not bounded on a comma b led us to a contradiction. So we must instead have that f is bounded on a comma b. And so this completes the proof. And so yeah, that's pretty much it for this video.